if you want to, build a massive solar farm that powers an entire city, the most stressful engineering problem isn't actually capturing the sunlight.
Right. The sunlight is the easy part.
Exactly. I mean, the real nightmare is figuring out how to build a, 500 megawatt glass sail out in the middle of a desert without a storm just ripping it right out of the dirt.
Yeah, the wind shear alone is terrifying.
Oh, it's massive. And since you sent us this industry breakdown from Eleanor Industries, they're an Indian aluminium extrusion supplier, we know you're already tracking the massive leap in renewable energy.
Right, and their report is, it's titled Aluminium Standard Sections in Solar Panel Structures, a Growing Demand.
Yeah, that's the one. But today, we're going to basically look right past the shiny photovoltaic panels. We are completely ignoring the glass.
Totally ignoring it.
Because our mission for this deep dive is to uncover the unsung structural hero of the renewable energy revolution. I mean, the reality is everyone obsessively looks at the solar cells.
Oh, no, absolutely. They care about efficiency,
Yeah.
wattage, all that.
Right. But none of it matters if the framework holding them up against, monsoons, scorching heat, and gravity just totally fails.
And the numbers really back up just how high the stakes are here. The source material highlights India's aggressive push toward a 500 gigawatt renewable energy target by the year 2030.
500 gigawatts. That's almost hard to wrap your head around.
It's massive.
Yeah.
We're talking about millions of installations.
Yeah.
And that spans from, small flat rooftops in a really dense city like Rajkot to absolutely massive horizon-spanning solar farms out in the deserts of Rajasthan.
Wow.
Yeah. So when you're deploying technology on that kind of continental scale, the structural integrity of these systems isn't just a secondary concern. It's a multi-billion-dollar engineering puzzle.
Okay, let's unpack this, because ignoring the mounting structure to focus only on the solar panel is, well, it's basically like buying $1 million high-performance hypercar and then deciding to save some cash by putting it on cheap, bald bicycle tires.
That is exactly what it's like, yeah.
Right. Like, if the foundation fails, the whole system collapses. It doesn't matter how efficient your solar panel is if it's lying face down in the mud after a bad thunderstorm.
And they do end up in the mud if they aren't engineered right.
Which is a disaster. So to understand how these structures actually survive decades of abuse out in the wild, we first really need to understand how they're made.
Right.
And according to the breakdown from Eleanor Industries, the most prized commodity in solar engineering isn't actually strength, it's predictability.
Predictability is everything.
Yeah, and that predictability comes down to a manufacturing process called aluminium extrusion. So, how does that actually work?
So to really understand extrusion, you have to picture the raw material first. You start with a solid cylindrical block of aluminium alloy, which is called a billet.
A billet, okay.
Yeah, think of it like a metal tree trunk. Now, you don't melt this billet into a liquid. I think that's a common misconception.
Oh, wait, really? I always just assumed they melted it down like in a foundry.
No, not at all. Instead, you heat it up to roughly 400 or 500 degrees Celsius, so it becomes highly malleable. It's soft, but it's still solid.
Okay, so it's glowing hot but holding its shape.
Exactly. Then, using a massive industrial press that generates thousands of tons of hydraulic pressure, you basically force that heated billet through a shaped steel die.
Wow.
And what comes out the other side is a continuous, dimensionally perfect profile of whatever shape that die was cut into.
I have an analogy for this, and it's going to take you right back to childhood.
Oh, can't wait.
It's essentially a high-tech, heavy metal version of a Play-Doh fun factory.
Yes. That is literally the perfect way to describe it.
Right. You push the lever down and the Play-Doh squishes out into a perfect star shape or like a long spaghetti string. Except here, the Play-Doh is scorching hot metal.
And the lever is thousands of tons of hydraulic pressure.
Exactly. But wait, I have to challenge this. We're talking about massive structural loads out in the elements, right? You're telling me we are building the foundation of our energy grid by basically just squeezing hot metal out of a press. Doesn't squishing it like that compromise the structural integrity compared to, say, solid forged steel?
It's a really intuitive concern, but the physics of extrusion actually work in your favor here.
Oh, really? How so?
Because you aren't melting the aluminium into a liquid state, you aren't destroying its crystalline structure.
Oh, because it stays solid.
Exactly. The immense pressure of forcing that malleable metal through the die actually aligns the grain structure of the aluminium in the exact direction of the extrusion.
Wait, it aligns the grains?
Yeah, it's like taking a handful of tangled strings and pulling them tight so they all run perfectly parallel. That alignment gives the extruded profile incredible longitudinal strength.
Okay, so the process itself is actually reinforcing the metal.
Precisely. And the reason this process is the bedrock of the solar industry is standardization. I mean, think back to that 500 gigawatt goal.
Right, massive scale.
Yeah, if a project developer is installing, say, 10,000 panel frames across a 50 megawatt solar park, they're dealing with an unbelievable amount of material.
That's a lot of metal.
Right. So imagine a discrepancy of just a single millimeter in the width of a mounting rail.
1 millimeter, that doesn't sound like much.
It doesn't, but over the length of one panel, a crew won't be able to, force it to fit. But when you connect 20 panels in a row, that single millimeter compounds.
Oh, I see where this is going.
Yeah, by the 10th panel, you're off by a full centimeter. Suddenly, the bolting holes just don't line up, the clamps won't secure the glass, and the entire string of panels is structurally compromised.
Which means the assembly crew is stuck out in the desert trying to custom fabricate a fix on the fly.
Which is incredibly expensive.
Yeah, that completely destroys the notoriously tight profit margins of solar projects. But if these are perfectly standardized uniform shapes, why do developers care so much about who supplies it?
What do you mean?
Like, why does it matter if it comes from a major supplier like Eleanor Industries or just, some random regional metal shop down the street that bought an extrusion press?
What's fascinating here is that predictability at a massive scale requires massive industrial discipline. Like, any shop can push hot metal through a die.
Sure, anyone can buy the Play-Doh press.
Right. But maintaining the exact same temperature, pressure, and alloy purity across 10,000 miles of extruded rails, that is incredibly difficult.
Oh, right. Consistency.
Yeah, when a massive solar project is running on thin margins and tight timelines, you literally can't afford for a shipment of rails to arrive with, like a microscopic warp.
Or inconsistent purity that makes it crack under wind load 5 years from now.
Exactly. The structural guarantees provided by a premium extrusion supplier ensure that the metal will perform exactly as the mathematical models say it should.
So we have these perfectly consistent metal lengths being squeezed out of our industrial Play-Doh press. But, a straight line doesn't solve gravity.
It definitely does not.
And it certainly doesn't solve wind. So we need to look at how engineers use different geometric shapes to solve distinct physical challenges. Because the invisible forces attacking, say, a residential roof in a coastal city are vastly different from the forces attacking an open, windy field.
Oh, night and day. And form follows function perfectly in this space. The engineers aren't just picking shapes that look cool.
Right.
They are choosing a geometry to neutralize a specific invisible force. Let's break down the toolkit a bit. First, you have your angle sections, or L profiles.
L profiles, so shaped like the letter L.
Exactly. Simply two flat legs at a 90-degree angle.
Yeah.
These are the workhorses. They're used for perimeter frames around the individual panels themselves.
Okay, so the L shape gives you a rigid corner to protect the fragile edges of the glass panel from impact.
Right, while also giving you a flat surface to mount against the rails underneath.
Okay, so the L profiles are essentially the picture frames holding the glass.
Exactly like a picture frame.
There.
Then you step up to channel sections. These are extruded into the shape of a U or a C.
U or C.
These are your main mounting rails. Because if you just used a flat piece of metal across a 10-foot gap, it would bow under the weight of the heavy panels.
Just from gravity alone.
Yeah. But by extruding vertical walls onto that flat base, so creating a U shape, you drastically increase its bending stiffness.
Oh, okay.
The vertical walls resist that downward force of gravity, which allows the rail to span long distances without sagging in the middle.
That makes a lot of sense. And then there are T sections, shaped like the letter T, which I read are used for structural joints and serve as symmetrical mid-clamps to hold neighboring panels together.
Yeah, those are very common.
But the source material heavily emphasizes hollow tubes, too, both square and round. If a U-channel is so strong against sagging, why do we even need hollow tubes?
Hollow tubes solve a completely different physics problem. They solve torsion, or twisting.
Twisting.
Yeah. A U-channel is great at stopping downward sag, right?
Yeah.
But if the wind catches a massive array of panels from a weird angle, it tries to twist the entire structure.
Oh, like wringing out a towel?
Exactly. And if you twist a U-channel, it will eventually buckle. It's open on top. But a closed, hollow tube distributes that twisting force evenly around its entire perimeter.
So it's much better against twisting.
Exactly. When you need a high strength-to-weight ratio for the main ground columns that support the entire array, a closed hollow tube is basically unbeatable.
Which brings up a huge distinction in the Eleanor Industries report, right? The battlefield environment. Rooftop solar versus ground-mounted solar.
Very different battlefields.
Yeah, if you're putting solar on the roof of a commercial building, your biggest enemy is dead load weight. I mean, the building's roof slab was only designed to hold so much weight.
You can't just pile tons of steel up there.
Right, so you have to use thin-walled, lightweight, extruded profiles to get the stiffness you need without literally crushing the building underneath.
But if you move to a ground-mounted farm,
Yeah.
weight is much less of a concern. The ground can take it. Out in the open, wind exposure becomes your primary enemy. Wind basically behaves like water. It hits the ground, ramps up under the angled panels, and generates massive uplift.
It's basically trying to rip the entire structure out of the dirt like a giant kite.
Exactly like a kite. So for ground-mounted systems, engineers switch to heavy-gauge aluminum tubes and massive, thick eye sections that are anchored really deep into the concrete foundation.
Here's where it gets really interesting to me. We talked about those UNC channel profiles used for the mounting rail.
Yeah, the anti-sag rails.
All right. The report highlights that these channels often feature integrated T-slots. But wait, I have to push back on this.
Go for it.
If you are baking a continuous groove, like a T-slot, into a piece of metal that's hundreds of feet long, doesn't that groove actually weaken the structural integrity?
It sounds like it would, right?
It feels like you're creating a built-in breaking point, right, where the metal needs to be the absolute strongest.
Well, in a traditional manufacturing process, like if you were just cutting a groove into a finished pipe, it absolutely weakens it.
Right.
But remember, this is extrusion. The engineers use computer modeling to actually thicken the aluminum walls, specifically around the T-slot, during the extrusion process itself.
Oh, so they reinforce the groove as they make it.
Yes. They add mass exactly where the stress concentrates, which completely neutralizes the weakness. And the payoff on the construction site is just staggering.
What does the slot actually do?
A T-slot allows a specialized clamp to slide anywhere along that rail and then just lock down tightly.
So you don't have to drill holes.
You completely eliminate secondary fabrication.
Wow.
I mean, picture a crew of 50 workers out in the 110-degree desert heat trying to align drill bits perfectly on metal rails. They'd be drilling, what, 20,000 holes to mount panels?
That sounds like a nightmare. Bits break, hole strip.
Measurements are off by a millimeter, exactly. And when you drill, you leave bare, unprotected metal exposed to the elements.
Oh, that's true. You break the coating.
Right. But with the T-slot, there is no drilling. The assembly crew just drops the clamp right into the slot, slides it down the track to wherever the panel happens to sit, and tightens a bolt.
That basically turns a massive industrial construction project into building with Lego.
It really does.
That's brilliant. It's not just about the metal then, it's about eliminating huge amounts of labor hours.
Labor's a massive cost, yeah.
So, okay, we understand the shapes. But a brilliant shape is completely useless if the material it's made from just turns to dust after 5 years in the rain.
Which is why material science is so critical.
Which brings us to the elephant in the room. Why use aluminium instead of the cheapest, most ubiquitous building material on Earth, steel? I mean, we build massive skyscrapers out of steel. Why is aluminium the undisputed king of solar structures?
Well, it comes down to a few very specific engineering advantages, starting with the strength-to-weight ratio.
Okay.
Aluminium is roughly 1/3 the weight of steel.
So it's much lighter.
Much lighter. But when you use high-strength alloys, specifically designated as 6061T6 and 6063T5, the tensile strength of that aluminium actually rivals many structural steels.
Wait, let me stop you there. When you say 6061T6, like most people, that's just a random string of numbers and letters.
Fair enough, yeah.
What actually happens to the metal to give it that skyscraper-level strength?
So the T6 part is the secret sauce here. It means the aluminium has gone through something called precipitation hardening.
Precipitation hardening.
Yeah. After the metal is extruded, it's essentially baked in an oven at a very precise temperature, rapidly cooled, and then baked again.
Like tempering steel.
Similar concept, yeah. This highly controlled thermal cycle forces the alloying elements inside the metal, like magnesium and silicon, to form a microscopic, rigid crystalline structure inside the aluminium.
Wow.
It essentially locks the atoms in place. And that's how a lightweight metal, which we usually associate with, soda cans, achieves incredible structural strength.
I love that. So you get the strength of steel at basically a third of the weight.
Exactly.
But there's an even bigger advantage when it comes to the elements, right? Because using steel outside is, well, it's like sending a knight into battle in standard iron armor.
It's strong, but but it rusts.
Right. If it gets scratched, water gets in, rust forms, and the metal slowly rots away from the inside out. It's like a high-maintenance pet. It requires constant grooming, painting, rust treatments, inspections.
It never stops.
Right. But aluminium is more like a superhero with a regenerating force field or a self-cleaning oven.
The superhero analogy is surprisingly accurate. The science behind that regenerating force field is called passivation.
Passivation.
Yeah. Aluminium naturally forms a microscopic oxide layer on its surface the very millisecond it is exposed to oxygen.
Wait, so it oxidizes immediately. Isn't oxidation just rust?
Yes and no. Unlike steel rust, which is very porous, flakes off, and exposes more raw metal to decay, the aluminium oxide layer is hard, impenetrable, and self-repairing.
Oh, so it seals it.
Exactly. If you drag a heavy tool across an aluminium rail and scratch it deeply, a new oxide layer instantly forms over the wound.
Instantly.
It literally heals itself before corrosion can even start to take hold.
That is practically a superpower for a framework that has to sit outside for 25 years.
It really is.
It makes it completely corrosion resistant, even if you build your solar farm in the salty air of a coastal city or right next to a highly polluted industrial zone. You just install it and forget about it.
And we also have to factor in thermal stability.
Because it gets hot.
Right. Out in the sun, metals expand and contract as they heat up during the day and cool down at night.
Sure.
If a rigid steel frame expands too aggressively, the sheer force can literally shatter the delicate glass solar panels it's holding.
Oh, that makes sense. The frame expands, the glass doesn't snap.
Exactly. But aluminium handles this thermal shifting beautifully, especially when combined with those slotted connections we talked about, which allow the metal to slide and breathe as the temperature fluctuates.
That's incredibly smart.
Plus, it's completely immune to UV degradation. The harsh ultraviolet radiation from the sun will eventually destroy industrial plastics and degrade certain composites, but aluminium doesn't react to it at all.
Which actually brings us to the environmental side of things. I mean, this is the renewable energy sector after all.
True.
The Eleanor Industries report points out aluminium's supreme recyclability. If you take an old, decommissioned aluminium frame, melt it down, and extrude a brand new one, it only takes about 5% of the energy it took to create the original aluminium from raw ore.
That's right.
5%. That's a 95% energy savings.
If we connect this to the bigger picture, you start to see why the industry standards shifted so dramatically away from steel.
Yeah, the math is undeniable.
When a project developer looks at the economics of a 25-year lifespan, the near-zero maintenance costs completely change the return on investment.
Right, the ROI.
Yes, you're going to pay slightly more for premium extruded aluminium on day one. But over the next quarter century, you spend $0 on rust inspections, $0 on repainting crews.
Which adds up.
And at the end of the project's life, you have a massive scrap value waiting for you because of that incredible recyclability. It perfectly aligns with the ESG, environmental, social, and governance goals of green energy projects. You're building clean energy with a clean, circular material.
Okay, you're making it sound like the perfect, miraculous super metal.
I mean, it's pretty good.
But there's always a catch when project managers and engineers are actually sweating over the blueprints and the budgets.
Sure.
Let's look at the real-world engineering and financial trade-offs that people in the industry actually have to wrestle with every day.
You're right. Nothing is without its hurdles. And the sources outline 3 major challenges that project developers have to navigate. The first is exactly what you just hinted at, initial cost.
Right.
Heavy-gauge structural aluminium simply costs more upfront than standard structural steel. It just does.
So what does this all mean? If a contractor is bidding to build a massive utility-scale solar farm, and their bid using aluminium is noticeably more expensive on day one, how do they justify winning the bid over a competitor who is just using cheaper steel?
That's a tough sell sometimes.
All right. Why wouldn't the client just take the lowest initial price?
They win the bid by forcing the client to look at the total life cycle cost analysis. It's essentially the secret weapon of a good EPC engineering, procurement, and construction contractor.
They show them the long math.
Exactly. They show the client the math over 3 decades. They sit down and say, yes, my competitor's steel is cheaper today, but in year 5, you have to pay a crew to strip and repaint it. In year 10, you have to replace rusted joints. In year 20, it's worthless scrap.
Ah, okay.
The aluminum bid is higher on day 1, but it is substantially cheaper by day 9,000. But it requires a sophisticated client who understands long-term operational expenditures versus upfront capital expenditures.
That makes sense. It's basically an education problem as much as a bidding problem. So what's the second catch?
The second challenge is design complexity. As the industry moves to gigawatt-scale projects, we are dealing with incredibly long spans between columns and solar arrays built on rolling, complex terrain instead of just, flat ground.
Right, you can't just put these on a perfectly flat parking lot anymore.
Exactly. So standard off-the-shelf parts aren't always enough to handle the unique wind shear of, say, a specific valley. Engineers have to get deeply technical, using something called finite element analysis, or FEA.
FEA, so they aren't just guessing based on standard load tables.
Not at all. FEA is advanced computer modeling that simulates exactly how wind and weight will stress a custom shape.
Like a wind tunnel in a computer.
Basically, yeah.
Yeah.
Imagine looking at a computer screen showing a cross-section of a metal rail. The software applies a simulated 100-mile-per-hour wind. Suddenly, a tiny corner of that rail turns bright red on the screen.
Oh, indicating a stress point.
Indicating a catastrophic stress concentration, yeah. So the engineer can then thicken the wall of the extrusion, die by like 0.5 millimeter in that exact spot,
Yep.
and run the simulation again until the red goes away.
That's amazing.
They use FEA to design complex, custom extrusion dies before a single ounce of metal is ever heated. It requires highly specialized engineering talent to get it right.
It's incredible. You are literally designing the structural DNA of the solar farm inside a simulation before the physical material even exists.
Exactly.
And that brings us to the third catch mentioned in the Eleanor Industries breakdown, material environment selection, which is basically the idea that not all aluminium is the same.
This raises an important question for you, the listener, to consider when you think about these massive infrastructure projects. Environment dictates chemistry.
How so?
You can't just open a supplier's catalog, point to a standard rail, and order 10,000 of them without analyzing where they're going to live for the next 30 years.
Right, you mentioned the coastal cities earlier.
Yeah, let's say you're building a solar farm right on the coast. The salt in the ocean air will aggressively attack standard aluminium alloys. You specifically need marine-grade 5XX series alloys.
Wait, 5XX series? How does changing the series actually stop the salt from eating the metal? Like, what does that do?
It comes down to altering the metal at a molecular level. In the 5XX series, magnesium is the primary alloying element.
Okay, more magnesium.
Right. When you add magnesium, it fundamentally alters the molecular lattice of the aluminium. It creates a specific type of oxide layer that chloride ions, which is the corrosive part of salt water, simply cannot bond to.
Oh, wow.
If the chloride can't bond, it can't hit the surface, it just bounces off. Conversely, if you're building inland but you want maximum structural rigidity, you might opt for specially anodized 6XX series profiles.
And if you're in an industrial zone, you might be dealing with a chemical plant exhaust raining down on the panels for 3 decades.
Which is highly acidic.
Right, so you need a completely different chemical resistance profile for that.
Exactly. This is why a project developer has to partner with a supplier who actually understands metallurgy. A supplier like Eleanor Industries isn't just pushing generic metal out the door.
They're customizing the chemistry.
They are analyzing whether your specific alloy will be breathing salt spray, fertilizer dust, or city smog for the next 30 years and formulating the chemistry of the metal to survive that specific diet.
It's just staggering how much invisible complexity goes into something most people just assume is a basic metal rack holding up a piece of glass.
It really is an unsung hero.
To wrap this up, I think we've firmly established that standard aluminium sections are the literal foundation making the global leap to renewable energy possible. I mean, it's the high-tech Play-Doh press of the industrial world, right?
I'm never going to forget that analogy.
It's perfectly stamping out standardized shapes that allow us to build massive energy infrastructure with speed, precision, and durability. Next time you drive past a solar farm on the highway or you see a new rooftop array going up in your neighborhood, you won't just see the shiny glass anymore.
You'll see the engineering underneath.
Exactly. You'll understand the intricate, perfectly extruded structural ecosystem that is silently holding the future of energy in perfect alignment against all the elements.
It fundamentally changes your perspective on the built environment, I think. You stop seeing a static, boring object, and you start seeing an active triumph of engineering just holding its ground against invisible forces, decade after decade.
Absolutely. And I want to leave you with one final, slightly provocative thought to mull over.
Oh, right.
We talked extensively about how aluminum is endlessly recyclable, taking just 5% of its original energy cost to melt down and reuse.
Yep, the 95% energy savings.
Right. So think about the hypercar and the tires analogy from the beginning. We put so much effort, engineering, and capital into building the perfect foundation today. Consider the world 25 to 30 years from now, when these massive initial solar installations finally reach the end of their life cycle and the glass panels degrade.
They'll all need to be replaced.
Right. Because the foundation is perfectly recyclable aluminum, could today's sprawling solar farms essentially become ready-made above-ground mines?
Oh, wow.
Like the clean building materials for whatever the next leap in advanced human infrastructure looks like might already be sitting right there, shining in the sun.